Find a formula for Riemann sum obtained by dividing the closed interval into n equals subintervals and using the right-hand endpoint for each x sub k. Then find the area by taking the limit as n approaches infinity. And we're given the function f of x is equal to 4x on the closed interval where x is greater than or equal to 2, less than or equal to 6. So we are letting n be equal to the arbitrary number of subintervals. And we're going to go ahead and let our closed interval here, x naught to x sub n, be defined as what's given, 2 to 6. So we can calculate our width. So we know that delta x is the length of the interval divided by the number of subintervals. So we have 6 minus 2 over n, which leaves us with 4 over n. And again, we are going to confirm this width using our kth subinterval. So that being said, let's find those subintervals. So again, we are dividing up our given interval here, 2 to 6. So our first subinterval starts at 2, and then we know, or we're thinking to ourselves, all right, 2 plus the width, which is 4 over n. And since this isn't super pretty, we're just going to leave this. You could find a common denominator if you want, but I'm going to leave it like this for now. So then our next subinterval is going to start at 2 plus 4 over n. And again, we're thinking to ourselves, okay, so we need to take this endpoint, 2 plus 4 over n, and add another width to it. So we're adding another 4 over n. So I'm going to leave this as 2 plus 2 times 4 over n. Or you can think of that as 8 over n. But then I'm keeping it in this formation to help us with our kth subinterval. So let's find one more interval here. So again, we're taking that endpoint 2 plus 2 times 4 over n, and we think in our heads, okay, if we take this interval 2 plus 2 times 4 over n, and we add the width, our next endpoint is going to be 2 plus 3 times 4 over n. So hopefully you're starting to see the pattern here. Right? We've got 1 times 4 over n. Next we have 2 times 4 over n. Next we have 3 times 4 over n. So when we continue this to that kth subinterval, so I think here it might even be easier to think in terms of the right-hand endpoint first. It's going to be 2 plus k times 4 over n. And so the left-hand endpoint has to be 1 less than that. So it would be 2 plus k minus 1 times 4 over n. And then we continue until we get to that very last subinterval. Again, using that same logic here that we did for the kth subinterval, we'll have 2 plus n minus 1 times 4 over n to 2 plus n times 4 over n. And again, we know we always want to simplify that last endpoint. We're trying to get 6. So let's see, those n's will cancel each other out. And we get 2 plus 4, which is 6. Woohoo! So we can remove this and put in that 6 there. So again, this is the way to check our algebra. And the most important subinterval here is always that kth subinterval. And in particular, we're going to be interested in the right-hand endpoint. So we can now use this kth subinterval to find the width and the height. So we use our kth subinterval to find the width and the height. So our width, delta x sub k, is the difference of the endpoints, x sub k minus x sub k minus 1. So we have 2 plus k times 4 over n, and we're subtracting 2 plus k minus 1 multiplied by 4 over n. All right, so this looks a little nasty, but it's not too bad. So I'm going to leave this first term as it is. That's 2 plus k times 4 over n minus, keep that negative on the outside. And what I'm going to do here is right hand distribute this 4 over n through to the minus 1 and to k. So it's going to be 2 plus k times 4 over n. And then we have minus 1 times 4 over n. And so now we can go ahead and go back here and we'll take this negative and we'll distribute it through to each term. And then look at all this fabulous cancellation. We've got 2 plus k times 4 over n. And then we have a minus 2 minus k times 4 over n. And then negative times a negative leaves us with plus 4 over n. And so we see 2 minus 2, those guys cancel each other out. Positive k times 4 over n minus k times 4 over n, those bad boys cancel each other out. And we are left with 4 over n, which is what we wanted. Woohoo! So we've confirmed our width. So this is the width in the kth subinterval. We need the height in our kth subinterval. So f of x sub k. So our kth subinterval, again, we're using that right-hand endpoint. So that's going to be f of 2 plus k. And I'm just going to rewrite this as k times 4 over n. So plugging this into our function, it's going to be 4 multiplied by 2 plus 4 times k over n. And we can take this 4 and we'll distribute it through to both terms to get our simplified height. We'll give ourselves plenty of room here. Oh, here we go. So if we distribute that 4 through, we're left with 8 plus 16 times k over n. So we have our width, and now we have our height. So we're ready to go ahead and find a formula for Riemann sum. Find a formula for Riemann sum and simplify it using the algebraic properties of finite sums so that we can apply the limiting process. So we know that the area is approximately equal to the sum from k is 1 to n of the height of that kth subinterval multiplied by the width of the kth subinterval. So this is the sum from k is 1 to n of the height we just found, 8 plus 16k divided by n multiplied by the width, which is 1 by 4 over n. And we want to simplify this. So I'm going to take this 4 over n and distribute it through to both terms of the height. And so this becomes the sum from k is 1 to n of, we have 32 divided by n plus 16 times 4 gives us 64 over n squared multiplied by k. And again, the reason I'm writing it like this with the k pulled out is because k is the variable of the general formula for our summation. So, keeping that in mind, we're now ready to apply the algebraic properties of finite sums. So we can rewrite this using the sum or difference property. We can think about this as the sum from k is 1 to n of 32 divided by n plus the sum from k is 1 to n of 64 over n squared multiplied by k. So again, keeping in mind here that k is the only variable, we can pull everything else outside of our sigmas. So we can rewrite this as 32 divided by n multiplied by the sum from k is 1 to n. And technically there's a 1 in there, but we don't even have to write that. Then we have plus 64 divided by n squared multiplied by the sum from k is 1 to n of k. So we can see two of those algebraic properties. The first one here is that constant rule. And looking at our second sum here, we see that this is the sum of the first n integers. So we can apply those rules and further simplify. And let's give ourselves plenty of room here. So we can rewrite this first one as 32 over n. And by the constant rule, we know that the summation just goes to n. And for the second sum, we have 64 divided by n squared. And by the sum of the first n integers, we know that this is multiplied by n times n plus 1 all over 2. And we can simplify. So let's see, these n's cancel each other right out to 1. We know 2 goes into 64 32 times. And I'm going to go ahead here. Well, we could simplify this however you want. I'm going to go ahead and say one of these n's, cancel with one of the n's in the denominator, which leaves us with 32 plus 32 multiplied by n plus 1. And this is all over n. So we can distribute this n in the denominator through to each term in the numerator. So in other words, you have 32 plus 32 multiplied by n over n plus 1 over n. So the n divided by n goes to 1, leaving us with 32 plus 32 multiplied by 1 plus 1 over n. And we could take this one step further. We can pull a 32 out of each term here. So this becomes 32 multiplied by 1 plus 1 over n, which leaves us with 32 multiplied by 2 plus 1 over n. Whew! So this is the general formula for Riemann sum. And we've set ourselves up beautifully here to go ahead and apply the limiting process. So we can say that the area is the limit as n approaches infinity of 32 multiplied by 2 plus 1 over n. And we have that reciprocal here. We know that 1 over infinity goes to 0. So this leaves us with 32 multiplied by 2 for a beautiful final answer of 64. So therefore, the area is equal to 64 square units by Riemann's limiting process.